Hello there, and welcome to the Construction Revolution podcast. My name is Eric E., and here on the show, we explore the latest trends, technologies, people, and organizations that are revolutionizing or disrupting the construction industry and changing what the industry will look like tomorrow. Today on the show, I'm speaking with Jeremy Gregory. Jeremy is a research scientist in the Department of Civil and Environmental Engineering and the executive director of the Concrete Sustainability Hub at the Massachusetts Institute of Technology. He studies the economic and environmental implications of engineering and system design decisions, particularly in the area of material production and recovery systems. His research topics include product and firm environmental footprinting, manufacturing and lifecycle cost analysis, and characterizations of sustainable material systems. Jeremy has applied these methods, often with industry partners, to a range of different products and industries including pavements, buildings, automobiles, electronics, consumer goods, and waste treatment and recovery. He received his PhD and MS from MIT and BS from Montana State University Bozeman, all in mechanical engineering. I'm excited to talk to Jeremy, and we'll hear more from him just after this. So over the course of your career, what changes have you seen in how the construction industry or even academia pursue the development of technologies that allow for more sustainable building materials?
I'd say one of the biggest changes is really just that people are talking about sustainability at all. I think that when it comes to topics of sustainability, the construction sector has really lagged other sectors in terms of making it a priority. And, I would say, generally, I put sustainability in the category of, motherhood and apple pie. Like no one's against it. Everyone likes it. But, there's a difference between that and like having it be a real driver of your activities. And I think kind of that's how the construction sector has viewed sustainability. It's something that everyone would like to take credit for, but it hasn't really been a primary driver of decisions. And so what I think, and that's the part that I think is really changing recently, is that it really is starting to be something that people are taking into consideration and starting to think more about, how do we make this a regular part of our decisions?
I've seen some talk of people or projects and even some Department of Transportation having sustainable guidelines in their project specs, which I think is a great step to kind of force some organizations to make these moves.
Yeah, we see that a little in the U.S. There's certainly a lot of interest by departments of transportation and sustainability. I participate in this Sustainable Pavements Technical Working Group that is organized by the U.S. Federal Highway Administration. And there's a lot of transportation agencies that are in that. But having said that, there aren't really a lot, at least in the U.S., that are explicitly taking that into consideration when making decisions. And I differentiate, kind of broadly using sustainability. By that, I mean more like life cycle environmental impacts of, let's say, like in that case, pavements. Of course, there's a lot of local environmental considerations that they're taking into consideration in different projects. But that's different than thinking about, sort of like what are the climate change impacts of the materials that I use and the way I design and maintain my pavement. So that's still a bit new. I would say that when it comes to construction materials, that in the U.S. at least on the building side is where we're seeing more pull in terms of taking environmental related considerations into materials and design decisions.
Well, when you talk about the design decisions, one thing that I find, like you mentioned, there's a lot of focus on the design side and the building side. But one area that I think has been kind of overlooked, but it's getting more attention, is what we do with materials once projects have been completed or there's some kind of tear down. Can you touch upon what the materials recycling infrastructure looks like in the U.S., maybe broader?
Yeah, sure. I think a lot of people don't realize that we actually, at least in the U.S., generate more construction and demolition waste than municipal solid waste.
Hmm.
And part of that is just because it's so darn heavy,
Yeah.
so there's a lot of it, but there's actually, a lot of that construction and demolition waste is concrete, and there's quite a bit of reuse of concrete as what we call recycled concrete aggregates, or RCA. So I think, at least on the one hand, that's good, and that's because sometimes it can be used to make new concrete, but a lot of times it's just used in applications where we need aggregates, which in the construction sector is plenty, like for road base, and so that can be good because it prevents us from having to extract new aggregates. But there still are a lot more opportunities to improve the materials collection and then reuse within the construction sector. I think we're still quite a ways away from having more of a circular economy type mindset in the construction sector.
Let's learn a little bit more about your findings in your recent work on the carbon uptake of concrete in the U.S. pavement network specifically. Could you explain your findings, particularly on how CO2 can be sequestered by the network?
Sure. Yeah. This is basically part of a phenomenon that has been studied for a long time called carbonation in concrete. And it's basically there's a chemical reaction that naturally takes place slowly in concrete over time, where it absorbs carbon dioxide and then it gets chemically transformed to be part of the mineral structure of the concrete. And that's something that engineers have been studying for a long time, because in the past there has been a potential for it to cause problems if there's cracks in the concrete, and if there's reinforcing steel, then that carbonation can lead to durability related issues. But it certainly doesn't have to. Properly designed concrete, it can have this carbonation and still perform just fine. But people have started to make some estimates on just how much carbonation is happening in concrete as we think more and more about climate change. And so there's a few reasons why the amount of carbonation that takes place, or we call it carbon uptake, why it varies. And a couple things. It really depends on how much exposed concrete there is. So obviously you have to have the concrete exposed to the air. So if you have a building where you have siding on it, you're not going to get as much carbon uptake as an exposed concrete. If it's painted, if it's depending on the climate, and also depending on the kind of mixture that you're using, those are all factors that can affect how much carbon uptake that you can have. So in the study that we did recently, we chose pavements because it's a bit more straightforward to estimate how much concrete is exposed, right? We have estimates of in the US how much exposed concrete pavements there are. And then we also have estimates of how much is what we call composite pavements, where it's most likely a concrete pavement that has asphalt on top of it. And as a consequence, so we know kind of the approximate dimensions of the concrete. And so we can estimate how much CO2 is absorbed during the life of the pavement. But it turns out there's also opportunities for carbon uptake when concrete reaches its end of life. And in particular, when you demolish it and open up all those surfaces, you drastically increase the amount of surface area that's then exposed to the air. And there's even more opportunities for carbon uptake. And so then when you talk about end of life, then there's all kinds of opportunities depending on, if you have concrete that's just sort of like in a pile, then there's a lot of that exposed stuff that's actually not, there's some exposed on the outside, but there's a bunch that's inside, as opposed to if you spread it out more, that increases the amount of carbonation. So we kind of made some approximations on some of those things, and then looked at the uncertainty associated with not knowing exactly what was going to happen. And that allowed us to then estimate just how much carbon uptake there was in the US pavement network.
So when the pavement has end of life and it's broken up and the carbonation increases, have you seen any applications of where that concrete could, for lack of a better word, live for the rest of its life in that kind of material?
Yeah. So obviously, there's all, even when that happens, the carbonation is really happening in what we call the cement paste. So this is, cement is what we start out with the powder in concrete. We mix it with water, it hardens, and that's what kind of the glue that helps to keep the aggregates and the sand together. So what happens when we break it up? We're breaking up that hardened cement paste. But what really is reused afterwards is the aggregates inside. So we try and crush it up and remove all that cement paste so we get the aggregates that we can reuse. But if you want the carbonation to take place, you want to spread it out where you've crushed it up enough to sort of create the rubble, but you don't want to remove all that cement paste yet. That's where you want to have even more. So if it's just sitting there absorbing CO2, it's not really going to have much of an application. But something that people have said is like we could crush it up, spread it out like in some landfills, let it sit there for a while, absorb some CO2 and then use it again. And so that kind of process, I've only heard of that really being used in a few Scandinavian countries. I don't think it's really used elsewhere like that. But that's the type of thing we wanted to understand just how much potential that there is. In which case, if we can create those kind of opportunities, then it could be beneficial.
Well, the fact that there's potential at all, I think, is fantastic. Because I think the concrete industry gets a lot of flack for being such a contributor, especially on the processing side when it's being created and things like that, all of the carbon that can be from that process. But the fact that it can absorb carbon similar to how maybe trees do, but to a different extent, I think that's a huge step forward for us to take in terms of trying to decide what to do with this material at different stages of its use cycle.
Absolutely. Yeah. And I think that's why we're trying to run these numbers, is just see how much potential is there throughout its life to absorb CO2 and how much is it, at end of life as well.
So I know your work discusses that California has unique climate conditions and even mixed design practices that result in like the largest carbon uptake during the use of pavement life. What are they doing differently than other areas of the country?
Yeah, it's some of it. There's a couple reasons why we found they had a significant amount of carbon uptake. And it's not just total amount. It was also one of the interesting things about California. When we looked at the breakdown of how much of the carbon uptake came from what we call the use phase while the pavement's in service compared to end of life was very different. So in a lot of places, the amount of CO2 uptake at end of life was more than the use phase. Whereas in California, it was the opposite. I think about 3/4 of the carbon uptake actually happened in the use phase. So a couple of reasons. One, they just have a lot of pavements in general, so that's kind of why the total number is like that. Texas also had a lot of CO2 uptake. But one of the things that's different is they had a lot more what we call a concrete pavement as opposed to a composite pavement. So what that means, there are a lot of states that have a lot of composite pavements, meaning that there's concrete underneath but asphalt on top. So you don't actually get that end of life. You don't get the carbon uptake until end of life when you demolish that and then expose the concrete to the air as rubble. Whereas in California, they have a lot of concrete pavements that are exposed to the air, so hence they get a lot more carbon uptake over its life. I mean, the climate plays a little bit of a role. The kind of mixtures that they use, they tended to use a little bit more cement in their mixtures, which actually helps when it comes to carbonation in terms of the chemical processes. But it's mostly just because they have more exposed concrete pavements.
That makes a lot of sense. So I guess on a related note, could you speak to your findings on the impacts of cool pavement and how we need to rethink our urban pavement strategy?
Sure. Yeah. For us, a cool pavement is basically a pavement that has a higher albedo or reflectivity. And albedo is a measure that ranges from 0, something that absorbs all energy and is basically perfectly black, to 1. and that reflects all energy and is looks perfectly white. A lot of new asphalt pavements, their albedo is it's pretty black, so it's on the order of 0.05 to 0.1. And so as a consequence, when we put those in a lot of urban areas, they tend to absorb a lot of heat, and that can contribute to the urban heat island effect, which is something where basically what it means is that temperatures in an urban area are measurably higher than they are in a nearby rural area. So obviously all the buildings, vehicles, things like that, contribute to that heat being there. So a cool pavement is something that's more reflective. It doesn't absorb as much heat. And there's many ways you can achieve a cool pavement. One, for those asphalt pavements, there's a lot of people who are putting coatings on them, and that can raise the albedo to say 0.3 or 0.4, which doesn't sound that high compared to 1, but it's pretty light gray actually. Like obviously we don't want it too reflective, and then everyone has to drive around with sunglasses on all the time. But as you know, being in Ottawa, certainly people do when there's snow on the ground.
Definitely.
So that's one thing you can do is put on the coating. There's also some ways you can change some of the aggregates that you use to have it be a little bit lighter. But it turns out that new concrete pavement also has an albedo around 0.3. And sometimes a little bit higher. And there are also different ways you can increase that albedo by, once again, using different aggregates or even different binders. There are like white cements that you can use to get it up to about 0.4 or higher. So these are all different strategies that can be used. And for a while, everyone kind of thought, people also have been looking at cool roofs in urban areas, which is also a similar thing. You just put, instead of like a black tar on the roof, you can make it reflective. And the benefit of that is that it means there's less heat being absorbed by the building, which means, you have to use more increased air conditioning. Now, it turns out the mechanisms for pavements to evaluate their impact on temperatures is a little bit more complicated, because particularly in urban areas, pavements can be in like a canyon. Mm-hmm. And what that means is that on the one hand, increasing the albedo, it has an effect where it lowers the air temperatures. So that's good, particularly in the summer. That means less, air conditioning in the buildings. But also when you're close by buildings, it means the radiation can bounce off the pavements and then go into the buildings. So meaning that actually that can also have an effect of increasing the amount of energy that's in the buildings and the amount of air conditioning. So what we've been doing is some research to look at how do you balance these various effects. The fact that the increased albedo affects what we call the radiative forcing of the climate, meaning kind of like the energy balance at our atmosphere. And climate scientists study this all the time with like melting ice caps. That's changing the albedos. If you do deforestation, that changes albedo and how that affects our climate. So changing a pavement albedo also affects the climate and generally leads to a cooling effect. But depending on where you are in a city, it can, as I mentioned, increase the amount of building energy consumption as well. So a lot of our research is figuring out there's some neighborhoods where the orientation and density of the buildings means it might not make as much sense. But there are some where buildings are more spread out where it would. But these are all kind of factors you have to take into account when trying to decide where's the best place to use cool pavements.
Wow, it sounds like a really interesting area for urban planners to kind of consider as they move forward, especially when, you look at buildings and how to kind of reduce the amount of carbon dioxide they emit. So you try to use things like renewable energy and things like that, where I would not have anticipated that what's going on outside the building can have such an impact on the performance or what goes on inside the building.
Yeah, absolutely. It's kind of a surprise to us. I mean, the thing I didn't mention is that actually, having a lower albedo like that can also help in the winter, right? So for some places, you also have to look at that dynamic. How are things different in terms of how it affects it could have a benefit, meaning there's less heating that needs to be done. So you have to sort of look at those trade-offs. And that's the same thing with cool roofs, right? If you have a more reflective roof, it just means that in the winter, it's not absorbing as much energy. But you have to kind of look at those trade-offs, and that's why it depends on what kind of a climate you're in, which sort of solution is going to make the most sense. But, another solution that I didn't mention when it comes to cool pavements is actually using what we call permeable pavements. And these are ones that basically, they have kind of more air content and are a bit more porous, and they're meant to basically absorb water. So like if it's raining on, like say a parking lot, the reason you have to have gutters all around it is because the water hits that parking lot. It's impervious to water. It goes off to the side and then goes down into our water treatment system. Well, a pervious pavement, the water goes in and it filters through the pavement and then goes underneath and basically goes back into the water table underneath that pavement. So it means you need a much lower amount of water treatment systems all around it. And also in areas where you're dealing with urban heat island, it can create a evaporative cooling effect, meaning that because there's water in the pavement, the water goes in there, and then as it evaporates going out, it creates a cooling effect. And so you can have both versions of that in asphalt and concrete. They can't really be used in areas where you have a lot of traffic, so you see them being used more in parking lots. But still, there's a lot of parking lots where that can be used. So that's another, interesting solution that people should consider.
Yeah, I'm just thinking of all the giant parking lots around malls and Walmarts and things like that could be utilized there.
Absolutely. Yeah, there's a lot of opportunity. And it's striking. Like we put one in our town, and one of the things they do to sort of test it out is take a fire truck and just, spray the hose on like a high pressure hose. And you see sort of a conventional parking lot, it just goes right off, as I said, to the edge. Whereas in the pervious one, it absorbs right in, and so it's kind of neat because it reduces sort of the like flood management that you have to deal with, particularly at like high precipitation events.
I'm curious, when you spray the fire hose, how quickly does it kind of dissipate where you can't see the water anymore?
Yeah. I mean, generally the ones that I've seen, it goes in pretty quickly. And I'm sure if you sort of look this up on the internet, there's all kinds of videos you can find where they've taken a cross section and then pour water into it. And, like I said, it's I'm trying to think of what's a good analogy, but it's like a sponge, where it has air holes in it, but it's set up so that it kind of filters through. So even if you're dumping it on top, it'll be dripping heavily underneath. So there obviously is only a certain amount that it can take at any given time, but because it can be spread out so much, that's what really helps. So, it can manage quite a bit of volume of water.
I'll definitely be looking at those videos after the show here. But Dr. Greg, I just have one last question before I let you go. And it's not entirely construction related, but I was very surprised to learn that only 8.4% of end-of-life plastics were collected for recycling in the U.S. in 2017. I would have thought that number would have been much higher because, I've grown up and always heard about reduce, reuse, recycle, and it seems to be so ingrained. So what impact is that number, and what kind of strategies do we need to improve our uptake?
Yeah, we've done quite a bit of research on the waste management system, and in particular on plastics recycling. And there's a couple different reasons as to why it's such a low number. Some of it has to do with just basically like technological limitations of recycling plastic. So like, for example, pretty much any metal can be recycled, infinitely, right? So like aluminum cans or, steel cans, like if producers could get all the material they needed, they would make, aluminum cans out of 100% recycled content. Whereas when it comes to paper and plastic, some of the sort of the chemical composition of it deteriorates over time. So you always need to add a little bit more what we call virgin content in order to create products. So that's one part of it. The other thing is just that for some kind of plastics, it's very energy intensive to actually transform them back into new products. And part of that is sort of, maybe you've heard this term of polymers. A polymer is like sort of the basic sort of chemical chain that makes up a particular kind of plastic. So like the number one that you see on the bottom of bottles, that's polyethylene terephthalate, PET. And that's sort of the basic polymer. But the difference between a polymer and a plastic is that they usually add some other chemicals to it to give it a certain kinds of property. That's why you can have PET bottles, you can have PET food containers, you can have clothing made out of PET. So those are the same basic polymer chain, but they're different plastics. And so that makes it hard to recover them, because when you get those plastics mixed in, you don't have like that pure PET stream. So PET is number one. Number two is HDPE, high density polyethylene. That's used in like milk jugs. Both of those have a relatively robust system for collecting and then treatment. And if you look at those two numbers, the recycling is higher. I think it's like, more like in the 20 some percent. The challenge is the other 5 numbers, 3, 4, 5, 6, 7, where 7 is other, right? There's just, like I said, because of those the limitations around being able to economically, in an economically efficient way, be able to turn those back into their original materials is difficult. And then sorting among them is also difficult. Like with the ones, it's kind of, it's a lot of bottles. The twos, it's a lot of milk jugs. Those are easier to sort. Whereas the other kind of packaging, it's much harder to sort. And then I'd say the other factor is just around collection. We're still, even though a lot of people are recycling, we're still, frankly, just not collecting nearly enough volume. Going back to the aluminum can example, I haven't checked this recently, but at one point, in the US, we used about 350 million cans per day. So meaning, about one per person per day. But we only collect, maybe half of those. And like, as I mentioned, that's why, the producers can't make, 100% recycled content. It's just because they don't get it all back. So we definitely need to improve our collection infrastructure around these things. If we can do sorting, that's also going to improve things. But that last one about sort of having economically efficient ways to be able to turn existing plastics into, or end of life plastics into new ones is still going to be a big challenge. And frankly, there just isn't a lot of incentive for producers right now to sort of redesign plastics so that they can be recovered and made into new products. So there's some real challenges there, and I think that's why the number is so low.
Sure. So I guess the only way to incentivize them might be through like societal pressure or through policy of some kind, I would think.
Yeah, I think it's both of those. One of the proposals that people talk about is called extended producer responsibility, or EPR, which is used in many different kinds of cases. But when it comes to plastics, it basically means either financially or in some other way, you make the responsibility of a product at end of life. You assign that responsibility to the producer. So it could mean the producer then has to invest in some of these other things, and that might incentivize them to change the way that they do things. But at least in the US, there's this very much this mindset that once the product goes to a consumer, it's a consumer responsibility. And that's why, as you said, that's a common mindset, and it's understandably so, because financially there was a transaction that took place and it becomes sort of property. But when it comes to sort of rethinking the way we do these systems, we might have to shift to more an extended producer responsibility type model to make significant gains.
Yeah, I think it's definitely a huge change in how we approach this problem and our mindset. especially in that relationship between producers and consumers, like you said.
Yes, yeah. I mean, there are models for it. Like Europe, for over a decade, has had extended producer responsibility models for electronics to try to improve recycling there. And so producers basically have a financial incentive there. There are many in the U.S. There are some states that also have an extended producer responsibility model for that, and that's being extended to other kinds of products as well. There are systems being discussed for pharmaceuticals as well,
Wow.
which sounds kind of funny, but there's a lot of concern about how people dispose of pharmaceuticals and if they make it into the water stream. If they are in the waste system, it's hard to get them out, and so that can affect marine wildlife and things like that. So that kind of model is definitely something that's gaining traction. But for it to work, you really need to have an engaged producers as part of that, and sometimes they are willing to come together, and sometimes it's more difficult.
Well, Dr. Gregory, thank you so much for coming on the show today. I've learned a lot, and I'm sure our audience has too.
Great. It's been my pleasure. Thank you.
Thank you.